Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Lisa Beth Kovitz. Today, we're going to look at how two versions of Star Trek Starship engines address speed of light limitations as they cross the galaxy. We're joined by Dr. Ethan Siegel, theoretical astrophysicist and author of Beyond the Galaxy and Treknology, the science of Star Wars from Tricorders to warp drives. You can find his shorter works on Forbes, Wall Street Journal, Scientific America, just to name a few. Welcome, Ethan.
Yeah, thank you. It's my pleasure to be here. Thanks for having me on the show.
In Star Trek Discovery, the spore drive requires a dip into something they call subspace. And interestingly, the concept of subspace appears only in three places: Star Trek, the BDSM community, and mathematics. For this discussion, we're going to skip the S&M and focus on the maths. What is subspace in mathematics, and does that reality have anything at all to do with how Star Trek is using the concept?
Okay, so in math and in physics, right, we have this concept of space, and in Einstein's theory, where you also have time there, we have this concept of space-time, and it's like the fabric of the universe. You put down matter and energy and it curves space-time, and that curved space-time then tells all the other forms of matter and energy in there, how do you move? The idea that there would be some sort of subspace would mean that, okay, most of the things, all the things we've observed in the universe, they go in the regular space, in the regular space-time, and they obey the rules we're used to. But maybe I can put down like some sort of imaginary shadow over space, and maybe some of the things in our universe can go into like this alternate set of rules, this alternate form of space-time, and they can, exit our universe, go into subspace and come back out, or they can abide by some of the rules of normal space-time and some of the rules of this, subspace, and maybe you can do something interesting with that. This is basically saying like, okay, we have the normal rules and we don't like what they give us, so let's put down something that has some other rules that isn't necessarily incompatible with what we've seen so far, and maybe we can do some real interesting things with that.
But mathematically, is the concept of subspace, it sounds like it's a placeholder for what you eventually will figure out later. Am I misunderstanding it, or is...
So what you're saying is, hey, like, we don't have any like experimental proof that subspace exists. We don't have like observational evidence for it, right? And that's fair. But you have to remember that a lot of these ideas, a lot of these sci-fi ideas that we've had for a long time, they predate physical discoveries of how we make it possible. So when we say, oh, I want to communicate faster than light, yeah, of course we do. Relativity doesn't allow that, but maybe there's a clever way that we can get there. Maybe there's a clever way to achieve that. And if the concept of subspace has any relevance for our real universe, maybe that's the key to unlocking it.
I am happy for you guys to work it out, and I just can't wait to reap the benefits of what you figure out. So with an understanding that the way Star Trek Discovery has set up their mycelium network is scientifically flawed, you wrote an interesting article about the use of the fourth dimension would make some of the elements of the mycelium network possibly work.
Yeah, so right now we say like, okay, there's like three spatial dimensions, and right, we can go length, we could go length, width, and depth, right? You have your three separate directions, right? You have how long something is, how wide something is, and how deep something is. Imagine if you didn't have three dimensions. Imagine if we lived on a flat two-dimensional surface, like you live on a sheet of paper, right? You can say, oh, I want to get from one side to the other side. And you're like, oh, we'll just go straight across. And I say, no, that's too slow. I don't want to go just across the space, because you two-dimensional nincompoops, you don't even know that there is a third dimension. And if I took this and I folded it, right? Now I can go from one end to the other, just flip, right? They're actually touching each other. So I can go from here to here like that by folding space. And that's kind of the concept of how instantaneous travel could be possible to a two-dimensional creature if it could access the third dimension, and to a three-dimensional creature like us if there exists and we could access a fourth dimension.
When?
When? When? Yeah. So we could get impatient, right? And be like, come on, where's my fourth dimension? Where's my instantaneous travel? Because what I really want to do right now is leave my house and go to that socially distant beach that no one else knows about and just go enjoy myself and this lovely May weather that someone is having somewhere. And you know, this is a really lovely dream, and one that you are not alone in saying, like, if this is even remotely possible, why aren't we working on this harder and trying to bring it into reality? And, you know, I could beg you for funding to say, yeah, we should be funding this. But I could also look at this and say, you know, it's important when you're developing something to use your imagination, to be creative, and to understand that what we know about physics and the laws of nature today are almost certainly not all there is. There is almost certainly more to learn. And it's very important to keep your mind open to all of the possibilities, no matter how unlikely they seem, that are out there. So when you're imagining the far future, some of these things that you say, okay, well, I can't rule out that it's possible, but I don't know how I'd make it possible. We don't know when those advances are going to come. But we do know for 100% certainty that if we don't imagine those possibilities and we don't start exploring them, they'll absolutely never come to fruition.
Dr. Siegel, do all of these models and ideas start out as math?
Not necessarily. Math is one way to get there. Math is like the tool, right? And it's an incredibly useful and powerful tool, but it's not always the only tool capable of doing the job. So when you say, can it be described by math? The answer is almost always yes. I don't know of an instance where something we've observed can't fundamentally be described by math. But mathematical endeavors and explorations aren't the only thing that lead to these new imaginings. Sometimes they come just out of left field, or just from someone's brain going on something, or from a phenomena that we saw that we can't explain.
Or from Captain Kirk?
Captain Kirk is his own unique thing. If you can fight God and win, there's no mathematics behind that that I know of. So Captain Kirk, you know, he has his own special case that whatever laws of physics he's on, I want them.
The first chapter of Dr. Ethan Siegel's very fun to read book, Treknology, describes Zephram Cochrane's year 2063 leap into the future using an Alcubierre warp drive. And yes, that is a plot line from the TV show Star Trek, but not all of it is fictional.
So Miguel Alcubierre was a graduate student in theoretical physics in the 1990s, and like many graduate students in theoretical physics, while he was writing his dissertation, he was procrastinating, because that is one of the things that people do. And one of his procrastination projects was to sort of say, hey, I know some general relativity. If I was interested in seeing if I can write down a mathematical space-time that describes warp drive, what will it look like? And in the mid-1990s, he actually turned this into a published paper and realized that, okay, if you want to take a starship to a place that's far away, you need to make sure that you don't destroy the space, that you don't have these like crushing forces in the space where your spaceship is, right? That would be really bad if you were like, you know, okay, warp one, engage, and everyone on your ship imploded. That's bad. So what Alcubierre did was he said, okay, if I can set up space in a particular way, and I need an enormous amount of energy for it, but don't worry about that. Don't worry that we don't have like a Jupiter's worth of antimatter to put into this spaceship right now. Just imagine you have infinite amount of energy and all the things you need. What he realized you could do is you could have a bubble, like a little sphere or spheroid of space that doesn't get bent. And if you want to go to your destination over in one direction, what you can do is you can keep this bubble constant, compress the space in front of you between you and your destination. So again, what was maybe 40 light years could shrink down to about half a light year. But there's a cost, and the cost is behind you. So in the direction you want to move, space gets contracted, but in the direction behind you, space gets rarefied, space expands behind you. So that's the cost. And he says, oh, well, you just make the bubble, you move in the direction you want to move, you get to your destination, you turn off your bubble. You got to make sure the bubble doesn't kill you when you turn it on and turn it off, but that's okay. We can do that. And then you want to come back and do the reverse thing. And this is great because it solves that earlier problem. If your journey takes 1 year, even though you're moving 40 light years, back on Earth, it also only takes 1 year because you are moving at warp speed. You're effectively moving through, you're covering a 40 light year distance in 6 months for both you and observers back at home. So that's a great solution. The problem is, when you start asking, what do I need to turn this mathematical solution into a physical solution? Because just because you could write something down doesn't mean it's necessarily real. What Alcubierre's solution requires, if we want it to be physical, is that we not only need energy in the universe to pump into this, we need a form of anti-energy or negative energy. And that's not something that we know whether that exists or not. The reason is, I told you, mass bends space in a certain way. If there were such a thing as anti-mass that would bend space like the opposite way, we don't know anything that can bend space the opposite way. But one possibility that's out there, and I love this possibility because it's very creative, is maybe because we've only measured gravity for normal matter, maybe antimatter anti-gravitates instead of regular gravitating. There's actually an experiment that's underway at this enormous complex in CERN where they have the Large Hadron Collider. They call it the antimatter factory because they produce more antimatter there than anywhere on Earth. They have taken antiprotons, the antimatter counterpart of protons, and they have taken positrons, which are the antimatter counterparts of electrons, and they've bound them together. And they've made anti-atoms, and they've contained these anti-atoms and measured their atomic spectra, which are the same as they are for normal atoms. And one of the things they're doing now is they haven't succeeded yet in making this measurement. They're trying to isolate these atoms, anti-atoms, so severely that they can have them at rest and then drop them and see in a gravitational field, just like normal matter, do they accelerate downward, or does normal matter go down and antimatter go up? We have not measured this yet. This is an exciting project. The leading experimental candidate to measure this is known as the ALPHA experiment going on at CERN. I mean, they're furloughed right now because of coronavirus and everything, but they are working hard on doing this. There are some estimates and expectations that either this year or next year, we will have our first results. Most people expect antimatter is going to gravitate just like normal matter does. And if it does, then that's probably not going to be how we achieve warp drive or an Alcubierre drive. But if antimatter anti-gravitates, which you never know until you measure it, then all of a sudden this goes from being a science challenge, from can science do this, to being an engineering challenge of, yes, science can do this, and now we have to build it. And that to me that's an incredible story. That's an incredible demonstration of the power of science and of theoretical imagining to say, like, this thing, if we make this experimental measurement, if we go and do this thing and we get this result, then this sci-fi dream can become reality.
Are those particles being manufactured or are they being discovered?
Oh, so first they were discovered. Now we can manufacture them. So they take right? Because at first we didn't know what was out there. When we started discovering antimatter particles for the first time, people didn't know what they were. When we predicted them mathematically in 1928 or so, a lot of people didn't think they were real. So first we discovered them, and now that we've manipulated matter well enough, we understand how to create them. Basically, if you take matter and you smash it together with more matter with enough energy, right? You've heard of Einstein's E equals mc squared. That means if you take enough energy, you can create mass that are brand new. You can create new masses, but the only way we know how to do it is you have to create an equal amount of matter and antimatter. So if I take 2 protons and I smash them together, which we do at CERN, then what I could get out is 3 protons and 1 antiproton. Same total number of protons, but I have 1 extra proton and 1 extra antiproton. Now I don't care what happens to these guys because you're boring normal matter. But this, the antiproton, so interesting. So we shunt it off to the side because it bends in a specific way. We slow it down, and then we take it with the electron's antimatter counterpart that we also create. We bind them together, and the ones that are neutral, we keep them, we slow them down, we confine them, and that's how we do our experiments.
But it sounds like all of these models and theories that make up warp drive and faster than light travel, more than just fantasy, require particles that may not have yet been discovered, but you're telling me are just about to be discovered.
Well, that's the whole thing, is we only know what's out there in the universe up to where we've looked, right? We have this not only this cosmic frontier of where we've gone and where we're trying to get to, we have these scientific frontiers about what we know and where the limits of what's been tested and what our knowledge is. If you had gone back even just a few decades and say like, oh, gravitational waves, we'll never detect those, but here we are detecting them because we came up with a clever experimental scheme to tease them out. You could have gone back 50 years and said like, oh, the Higgs boson, like, yeah, that's a clever theory, but where's that ever going to show up? And now we've built the technology that it can show up. So what lies beyond that? What exists at higher energies? What exists on larger cosmic scales or fainter cosmic scales than what we can see? What exists as we get closer and closer and closer to absolute zero? Are there going to be new phenomena that emerge at these scientific frontiers? As we've looked, every time we've looked, we've revealed more and more about the fundamental laws of nature and the things that are possible. I personally think that the more we look and the more we invest into pushing those fundamental frontiers, the more we're going to learn about what's possible. And if you look at what that has meant technologically, right, you can look at technologies we have today that were pipe dreams 50 or 100 years ago that are so ubiquitous now, we don't even think about them as being futuristic. When was the last time you walked into a grocery store or an airport, saw those automatic doors open and thought, I'm living in the future, right? We take them for granted now.
Alcubierre published his solution in 1994, and although most of us picture in 1996 James Cromwell in the role, it was all the way back in 1967 that Star Trek writer Gene Kuhn imagined the fictional Zephram Cochrane creating a functional mechanical version of what would eventually become this real life theory. Oh my God, Ethan, did we just prove that time travel exists?
I wish we did. That sounds like a good argument too. Like maybe Alcubierre had the solution, maybe Zephram Cochrane figured it out, and maybe he sent it back to a science fiction writer in 1967 who did this. Now, in reality, of course, people have been imagining these things since long before Star Trek was a thing, since long before even Einstein came up with relativity. There were people in the 19th century playing with geometry, how you could fold space. There was a wonderful book called Flatland that was written in the 1880s that talked a lot about 2 dimensions to 3 dimensions versus 3 dimensions to 4 dimensions, traveling through space, being able to do things and access things that are not possible in our 3-dimensional world. So I would say this is really a testament to the power of human imagination. and our capabilities of imagining worlds that never were and imagining new laws of physics and of nature that may or may not ever pan out. What's remarkable is how kind to us nature has been, that we have this phenomenal theory of gravity, general relativity, that ties together matter and energy with space and time, and that so many things, if we can just provide the right conditions, so many things are actually possible.
You know, in 1967, Star Trek writers placed humanity's jump to warp capacity and first Vulcan meet and greet in the year 2063, which is just 43 years away from the date this interview is recorded. So, Dr. Siegel, are we on schedule for that?
You know, I want to be the optimist. And so I'll say, if nature is kind to us, right? And we have no idea what that looks like. If nature is kind to us, if antimatter does anti-gravitate, or if we can create the Alcubierre bubble and warp drive through, some form of anti-energy, some way of bending space in a negative way, maybe it is, maybe we are on schedule. What it's going to take, though, is I believe it's going to take a worldwide investment in creating and building these phenomenal technologies that may or may not be physically possible. If we wanted to build something like this realistically, it would cost, more money than even the richest mega billionaire on earth has in their entire fortune. This is going to require a civilization scale endeavor. And
Well,
so I think a lot of it's
that's
going to depend on our will, right? Do we have the will to make this possible? I know Zephram Cochrane was just alone in his desert with a tin can and a bottle of whiskey, and he made it happen.
Well, I think that's why people like Star Trek also. It's not just because of the technology, it's because the world is um, so organized and so kind to each other, and all the worlds are pulling together in Star Trek. So I think that's part of the model that makes it so appealing.
That was one of the things that drew me into it too, is not just like, I've always loved space and science and physics and astrophysics, and this was a passion of mine long before I was ever introduced to Star Trek. I was wondering about all of this stuff as a even small child, and I've never lost my wonder for it. But with Star Trek, it brought in this additional element of ethics and morality and kindness and goodness towards others and the betterment of the entire enterprise of civilization. And that's what I thought was this wonderful fusion of things for me, of these lofty dreams of not only what we can achieve as a species scientifically and technologically, but also of what we can become as a species by being kind to each other, by working together for the betterment of all, and how far we can go if we're willing to think of the good of ourselves no higher than we think of the good of all of us.
You know, Ethan, it seems that in the past, the two avenues open to scientists were industry and university, and you seem to be carving out a different path.
Oh yeah, I mean, it's funny you say that because I'm like, yeah, I did them both, and now I don't want to do either one. Like I was a college professor for a number of years, and I did work in the private sector also for a number of years, but now I'm off. Now I'm off doing science communication and writing books and trying to basically be a translator for. I'm going to tell you how to go from like physics and astronomy into English, because I think that these are wondrous things that are happening in the universe, and everyone should know about them, whether you have a PhD in this specific field or not. The wonders and joys of the universe are for everyone, and I'm just happy for all the ways that I get to help bring those stories to the general public.
But it seems also, especially when you live in a democracy, that people need to understand science, or we end up in trouble.
I mean, I think we've gotten into trouble many times over very long periods of time, not just now, but you could argue especially now, but I'll say for all of history, where people are like, I think things should be this way, and I think things should be the other way. What science does is it gives you this broad knowledge set that everyone should be agreeing on, that there are some things that are objectively true about reality, and we will make better decisions, more informed decisions, and we will be better prepared to be compassionate towards one another when we all accept those scientific facts about reality. And if I can help make that possible, if I could help just push the ball forward a little more in that direction, I'm more than happy to do it. I think that's an unequivocal good.
Dr. Siegel, we are out of time. Thank you so much for visiting with us.
Thank you for making it such a pleasure. I really enjoyed my time here, and thanks for a wonderful conversation.
Dr. Siegel's other book that we didn't even get to scratch the surface of is called Beyond the Galaxy: How Humanity Looked Beyond Our Milky Way and Discovered the Entire Universe. It's 388 pages and about the entire universe, so you're going to have to come back and talk to us again.
No problem.